Okay, I think we have most of you here already. So if your friend is still not here, ask them to join quickly. Otherwise, when after I've started my lecture, I won't stop my lecture to admit anyone anymore. All right. Okay, I'm going to start with chapter 7a, right, on digital modulation techniques. So basically, I have to finish this chapter so that you have a good idea of your practical session this week, which is on digital modulation techniques. All right, so I hope all of you have got your MATLAB installed. Yeah. No more excuse that you're installing your MATLAB, your MATLAB not running, all these things during the coming practical session. Yeah. Okay. Wait. Lecture not available. I haven't uploaded me. Okay, let me check. I thought I had. Alamak. Let me see. Lecture. I say, forgot again. So sorry about that. Okay, let me upload first. I was busy marking your tests over the weekend. Then I kind of forgot about this. Okay, I have uploaded 7A. I need to check my 7B later on, then I upload this week. Okay. 1, 2, 3, 4, 5, 6, 7A. Yeah. Okay. Can you see your notes in your Google Classroom now?
Yes, Miss.
Okay. Thank you. Sorry, I forgot again. I have finished marking your test. The result, I think just okay only about 10 of you fail. All right, so some at the borderline. So what that means is you have to put in a lot of hard work in the second part of the coursework. All right, again, which is not as easy as your test. All right, so let's get started on chapter 7A. Okay, chapter 7A is about digital modulation techniques. So this chapter will just explain the concept of various digital modulation techniques. Then these are the subtopics in these chapters. So we're going to start with the transmission methods for analog and digital signal. So this will be an overview, and then followed by the modulation of digital signal. All right, then we're going to look at different classes of digital modulation techniques. Then after that, we're going to move on to three basic ones, which are the binary amplitude shift keying, binary frequency shift keying, and binary phase shift keying. All right, then we're going to move on to study another method, which is called differential phase shift keying. All right, this is a variation of binary phase shift keying. Then we're going to study about constellation diagram. Constellation diagram is related to phase shift keying. All right, then we're going to look at other types of modulation schemes, which is called Amnary modulation scheme. Then the last modulation scheme that we are going to take a brief look at is the quadrature amplitude modulation. All right. And I'm going to end this chapter with a short discussion on bit rate and baud rate. All right, so basically you need to know the difference between bit rate and baud rate in order for you to calculate the bit rate for any modulation scheme. All right, and then from here it should be able to work out the bandwidth. All right, so again we need to look at bandwidth. Another thing we need to be concerned with is the power as well. So bit rate is related to bandwidth as well as the power. So is baud rate. Yeah. Then learning outcomes for this chapter, basically three only. So the first one is you need to be able to describe and compare various digital modulation scheme. All right, draw constellation diagrams. Basically, this is for phase shift keying method. And also you need to be able to calculate bit rate and baud rate. All right, from here, then you should be able to work out the bandwidth as well as the power requirement. Okay, so this slide basically show you some transmission methods for analog as well as digital signal. So as far as this course is concerned, we started with analog signal transmission, right? Yeah, we have an analog signal, and then we can, this is normally baseband. Baseband signal, if we transmit it using analog channel, no problem. All right, that gives you analog output at the other end. But this is only for short distance, right? If you want to your signal to travel longer distance, then you have to modulate your signal. All right, so you need to modulate your analog signal, all right, so that it can travel along the analog channel. Yeah, and basically this is a wireless channel, right? And at the receiver, you need a demodulator, all right, a circuit to recover the signal and to give you the signal that you actually send at the source side. Then for digital, we actually studied this in the previous chapter. All right, when our signal is digital, all right, so we need to encode our signal basically to convert our strings of ones and zeros into waveform, right, electrical waveform, so that it can travel to digital channel. Again, digital channel is a wired channel, all right. Digital data cannot travel wirelessly. Yeah, digital data can only travel to wired channel, which is cable. And because we encoded the digital data at the transmitter side, so at the receiver side, you need to decode the data. All right, and this will give us the digital output at the destination here. Then, if we want to transmit our digital data wirelessly, all right, then you need to modulate your digital data. So this is what we're going to learn in this chapter. All right. So given digital data, we modulate this digital data for us to transmit it through an analog channel. All right, so we want to send our digital data wirelessly. Again, this is for over long distance or over even short distance where there's no wire involved. Yeah, and of course, at the receiver, you need to demodulate your signal and to recover your digital output. Okay, and in chapter six, we also briefly look at how we can convert the analog data into digital data, encode it for us to transmit it over digital channel, right? And at the receiver, we need to decode the digital information and convert digital to analog, right? Convert the digital signal to analog signal to produce the analog output at the receiver. Yeah, and the more complete, transmission path or communication system is the last one here. In the last one, we have real world data, which is normally analog. All right, and then we do analog to digital conversion, and then we encode it. So this will give us the digital information, but then we want to transmit this digital information over analog channel. So we have to modulate this signal, all right, and then so that it can travel wirelessly. And at the receiver side, because we modulate the signal, and then we need to perform demodulation at the receiver, and followed by decoding and digital back to analog conversion, and to give us the analog output at the destination. All right, and this is a one-way communication. And normally nowadays our communication are two ways, isn't it? Right. So if our communication are two ways, then from point A to point B, you have one path already. And now from point B back to point A, you need to set up another path. So that means you need to have a set of this is analog, so you need to have a set of ADC and encoder here. You need to have a set of modulator here, right? And then your information now is going to travel this direction. So you need to have a demodulator here, right? You just need to change the position of the block, and followed by the decoder and DAC over here. All right. So in the past, communication was mostly one way, but nowadays a lot of communication now are two way. All right. So therefore, your channel must be able, and your communication system must be able to take care of um, communication in two direction. Yeah, that's why a lot of our communication system now come with the two direction data conversion, all right, or signal conversion. So instead of having a modulator here, we have modem, right? Modem stands for modulator demodulator. All right, same for this one here. Yeah, so instead of having just one demodulator, you also have a modulator, all right, to allow signal to be transmitted from one end to the other end and vice versa. Right, so modulation of digital signal. So the modulation, the definition is still the same, right? The only difference now is we convert our digital data, right, to a band pass or high frequency analog signal. Yeah. Remember in uh, analog modulation techniques, so we talk about amplitude modulation or frequency modulations. We actually convert a low frequency analog information, right? Low frequency analog information into a high frequency analog information and analog signal. Yeah. So again, for digital signal modulation, we actually convert our digital signal or digital data, all right, to analog form. All right, and this is normally very high frequency as compared to the digital data itself. Okay, so the reason we do this is because we want to send our digital signal using a carrier. All right, same like our amplitude modulation and frequency modulation. We use a carrier to carry our information for us. So in this case, we want to use a carrier to carry our digital data. All right, so again, there are three basic types of digital modulation technique. The first one is called amplitude shift keying. All right, digital modulation normally end with the terms shift keying. All right, and then we have amplitude shift keying and phase shift keying. All right, the concept of these three are very similar to our AM, FM, and the phase modulation, which I did not actually cover in the analog part. But if you understand AM and FM, then amplitude shift keying and frequency shift keying should be no problem for you to understand as well in this chapter. All right, so the only thing that is slightly new in this chapter is your phase shift keying. Yeah. So application of this modulation of digital signal is for us to transmit data over a bandpass channel. All right, such as telephone lines. Basically, this telephone line we are referring to your optical fiber. All right, so this optical fiber now actually the channel has a very wide bandwidth, so you can actually transmit your data by the channel, by this channel at much higher speed. And also radio means is free space over the radio spectrum, right? Or optical channel. Optical channel again, we're talking about optical fiber here. Okay. Then we actually modulate our digital signal so that we actually limit the frequency range. All right. For the data to be transmitted. All right, so that we limit one transmission of one data to a certain frequency range only. Yeah, so that a lot of data can be transmitted over the radio frequency spectrum. All right, so it's like FDM in a way, which is frequency division multiplexing. Okay, these are the three basic classes of digital modulation techniques. Right, so we have amplitude shift keying, frequency shift keying, and phase shift keying. So in amplitude shift keying is similar to AM, amplitude modulation, where the amplitude of the carrier carry our digital information. Right. And then in frequency shift keying is the frequency of the carrier that carry our information. So we represent one with the frequency with the one frequency, we represent zero with another frequency. All right, and then phase shift keying, so we represent our binary ones and zero with different phase angles in the carrier signal. All right, and the extension to these three basic digital modulation techniques is the QAM. QAM is a combination of amplitude shift keying and phase shift keying. So basically, we make use of we actually change two parameters in the carrier, which is the amplitude as well as the phase angle of the carrier, in order to represent binary data. Okay, I'll go into each and every one of these in details later on. So in addition to these three basic one, okay, actually the three basic are these three, this ASK, FSK, and PSK, but we can have many levels. All right. So the most basic one is binary, which is just 1 and 0. And then later on, I'm going to study the M-NARI modulation schemes. M-NARI modulation scheme meaning we have more than 2 levels, not just 1 and 0. All right. So we're going to look at quadrature PSK, all right, or for PSK. And also we're going to look at QAM. Yeah, and from there, it should be easy for you to understand the 8 level, 16 level, 32 level, and so on. Okay, let's start with the binary amplitude shift keying or ASK. All right, so normally when we talk about ASK, we first talk about just two ASK. All right, 2 level. So the representation of this modulation technique is actually very simple. We only use 2 symbol states. All right. So here, if our looking at the binary 0 and binary 1 in our data, all right, when we need to transmit a binary 0, basically the modulated signal has nothing. It's 0 amplitude. All right. And to transmit a binary 1, we transmit a carrier with the amplitude A1. And the carrier, normally we just use the sinusoidal carrier lah. So in this case, we use the cosine signal. Yeah. So you can see that when we send a binary one, basically we turn on the carrier signal, and then when we send the binary 0, we just off the carrier signal. All right. So the graphical representation for this method is given here. Yeah. So we have let's say first bit is a 0. First bit is a binary 0. So there is nothing. We don't send anything. The second bit is a binary 1. All right. So we send a cosine signal. Yeah. The third bit is also a binary 1. So this is followed by a strings of cosine wave. Yeah. The fourth bit is a 0. So we send nothing. All right. So looking at the modulated signal, is basically we just turn on and turn off the carrier. Right. Turn on and turn off the carrier signal based on the binary information. Okay. So the line encoding will actually determine the value of the analog waveform. Yeah. So in this case, again, if you look at the line coding that I use here to modulate the carrier, this is what is this? On-off keying non-return to 0, isn't it? On-off keying non-return to 0. So it gives us the modulated signal in this manner. All right. And as far as the demodulation is concerned, we actually perform demodulation by detecting the presence and the absence of a sinusoid. So at the receiver, it's very easy. We just see whether got carrier signal or not. All right. If there is carrier signal, that means this is a 1 coming in. If there is no carrier signal, all right, then meaning it's a 0 that is coming in. Okay. So very simple detection method. So how to generate the binary ASK signal? So it's very simple. It's very similar to the double sideband suppressed carrier. We just use a mixer or a multiplier, right? So meaning we multiply our digital information, all right, with a carrier signal, which is normally a cosine or a sine wave, all right, to produce the ASK signal. Yeah. And then if you use this method, make sure your signal is your line code of your digital data is actually using OOK non-return to 0. All right. On-off keying no return to 0. Yeah. So this will give you, and then make sure your signal amplitude for your digital data is always positive. All right. Is always positive, and when 0 is actually 0 volt, and then when 1 is of a certain volt. Yeah. And so because if you look at the generation of this ASK signal, is very similar to the double sideband suppressed carrier modulation technique, isn't it? So what happened is the modulated waveform, all right, will have a bandwidth that is 2 times the baseband. All right, 2 times the baseband. So let's say this is a baseband spectrum, and why we get this shape? This is because it's a rectangular pulses. All right, rectangular pulses will have a sinc envelope in the frequency domain, isn't it? Yeah. So again, rectangular pulses has a very wide bandwidth, so you can expect in the frequency domain, you have a spectrum that lasts for quite a big range of frequencies. So the ASK spectrum, because the method modulation method is similar to double sideband suppressed carrier, so basically you can expect the spectrum to be double-sided as well. Okay, double side, you have double sideband. So meaning now in the modulated wave, all right, your ASK modulated wave will have a spectrum on the lower side of the carrier frequency and also at the upper side of the carrier frequency. Yeah, so that means you have upper sideband and lower sideband as well. Yeah, so you can expect the ASK bandwidth will be very wide as well. All right, will also be very wide. That's because your baseband signal and bandwidth is already wide because we use a rectangular pulses there. Okay, so in order to reduce the bandwidth, all right, remember from chapter 6, in order to reduce the bandwidth, we actually send the rectangular pulses through a pulse shaping filter, right? We also use a pulse shaping filter before we perform the multiplication. So that will reduce the bandwidth. Yeah. So on this graph on the right hand side here is when we use a raised cosine filter. All right. So that will limit your baseband spectrum to a much, much smaller bandwidth. All right. And hence, after modulation, your ASK signal will also have a smaller bandwidth, yeah, as compared to the rectangular signal here. Okay, then to recover the ASK signal, basically there are two methods. All right, same as our amplitude modulation. So the first one is a non-coherent detection by using envelope detector. All right, again, you can see this is very similar to IM. So incoming signal passing through a diode, all right, in combination with a capacitor, that will produce only the positive pulse. All right, no more negative. And then you pass it through a low pass filter that will remove the high frequency carrier. All right, leave only the envelope. All right, so the envelope basically represent our digital information unit. So all we need later on is just a thresholder here, or a comparator. All right, and you actually compare, set your threshold correctly, then you should be able to determine whether the incoming pulse is a 0 or the incoming pulse is a 1. All right, by looking at the amplitude. Okay, that's for coherent, non-coherent detection. So we can also recover the incoming signal by using coherent detection. All right, that means synchronous detection. So as the name suggests, synchronous detection require a local carrier here. All right, so we multiply the incoming signal with the local carrier. All right, and that will produce again a baseband signal as well as the signal at the 2 times the frequency of the carrier. All right, same as amplitude modulation recovery. Okay, and then what you do next is pass it through a low pass filter again. That will allow you to recover your baseband signal. All right, baseband signal now, pass it through a thresholder also. So same method, pass it through a thresholder or a comparator and to decide whether this is a 1 or this is a 0. And the comparator will give you a rectangular waveform, which represent the binary information. Okay, so this slide basically show you a bit of the mathematical analysis of the ASK frequency spectrum. All right, let's say now we are using a carrier signal, which is a cosine signal of frequency Fc or omega c. All right, and then we are using a unipolar signal to represent our digital signal. Unipolar meaning this is a rectangular wave, all right, which is on-off keying with non-return to 0. Yeah, so we only have a positive side. Then this signal can be represented with this Fourier series expansion. All right, I believe you have learned this from your previous courses. So for rectangular pulses, you only have some DC component, right? Why DC? Because our pulses are only on the positive side. So you have this DC component, and this is your fundamental signal frequency, and then followed by all the odd harmonics. Right, this is a Fourier series expansion of a rectangular pulses. Then the ASK modulated signal basically is a product of these two signals, the carrier with the digital signal. All right, so we multiply, put in the expression for the carrier signal, which is cos omega c. And then the next part is the expression for your digital signal. All right, so when you perform cross multiplication, you're going to have half cos omega ct, which is your carrier component. All right, followed by the product of the various frequency component in your digital signal with the carrier. All right, so this will give you, all right, again, we're going to make use of our trigonometry identity here. Cos A cos B equals to half of cos A minus B plus cos A plus B. All right, so this will give you, again, the common factor is 1 over pi. So this will give you this one will give you cos omega c minus omega naught t, and also cos omega c plus omega naught t. So this will give you a two side bands. All right, and the next product will give you another set of two side bands. Yeah, so as far as that's how you end up having a double side band here on this side as well as on this side after the multiplication. This is a very simplified, very much simplified spectrum, frequency spectrum plot now. Okay, so that is for ASK. All right, so in data communication, we normally use full duplex link. Full duplexing meaning we have communication in two directions. All right, one is for uh, from my place to your place. The other one is from your place to my place. All right. So if you actually check your what do you call that? Your Wi-Fi, you know, you have what upload speed, download speed. Yeah, that's the one. All right. One is upload. Upload means from me to you. Download is from maybe from you to me. Yeah. So as far as bandwidth is concerned, we need to divide the bandwidth into two. All right, with two carrier frequency. So in this case here, I have one carrier frequency for upload, right? Meaning from my place to your place. And we'll have another frequency for download, which is from your place to my place. Yeah, so this is for two-way communication. So that will leave us, let's say we have a 100 kilohertz bandwidth allocated for our communication here. So, and let's say we divide it equally, right? So 50 kilohertz will be for upload, 50 kilohertz will be for download. All right. So that means, and then because the ASK for each direction of communication, ASK required two times the baseband signal bandwidth, right? Two times the baseband signal bandwidth. This is for double sideband. So that leaves us only 25 hertz for our signal. All right, 25 kilohertz for our signal. And let's say we actually modulate our digital signal such that we use 1 hertz to transmit 1 bit, and therefore we can only have 25 a data rate of 25 kilobits per second in each direction. All right. So given a bandwidth of 100 kilohertz, in this case we have a bandwidth of 100 kilohertz. All right. The only one that the actual, all right, the actual bandwidth that we have, right, for our data is only 25 kilohertz, which actually translate to 25 kilobits per second here. All right. So you don't have a luxury of I give you 100 kilohertz, then you have 100 kilohertz. Yeah, or you means that you can actually transmit at 100 kilobits per second. No, that's not the case. And this is for ASK. All right, this is for ASK. Later on, we're going to look at a different modulation technique that can actually give us maybe better bit rate with the same bandwidth. All right. Okay, the advantage of ASK or binary ASK is first one, of course, is very simple to generate, very easy to generate, isn't it? Just multiply your digital data with carrier waveform. Again, the problem with ASK is the same as the problem with AM, which is very susceptible to noise. Okay, because noise will actually change the amplitude. But compared to AM, it's not as bad. All right, because you only have two levels, whether you have or you have amplitude, you have a carrier, or you don't have a carrier. But if your carrier amplitude is relatively large as compared to noise, this system can still perform quite well. All right. So therefore, ASK is normally used to transmit digital data over optical fiber, because optical fiber has very low noise. Okay. All right. So any question on ASK so far? No.
No, Miss.
All right. So let me see who want to emit. Left already. When I was teaching just now, there was some disturbance. Okay, let's ignore him. All right, so let's move on to FSK. So we're going to look at the binary frequency shift keying. So as the name binary suggests, we use two different frequency. All right, so take for example, here I'm going to use frequency 1 to carry a carrier of a frequency F1 to carry data that is binary 0. All right, and then to carry binary 1, I use a carrier with frequency F2. All right, so the binary shift frequency shift keying basically make use of two frequencies or carrier, two different carriers, one carrier to carry 0, one carrier to carry binary 1. So now, if you look at this diagram over here, okay, I have the data which is 1, yeah, and then I follow by 0 here. So I have two carrier. All right, carrier number 1 has a lower frequency as compared to carrier number 2. All right. So what I do is the FSK signal to carry a 1, I use a high frequency carrier. All right. To carry the binary 0, I use a low frequency carrier. All right. So the frequency of the carrier basically represent whether this data is a 1 or this is a 0. So it's actually very, very easy as well, that's concept-wise. Amplitude is the same. All right. For both carrier, we use the same amplitude. And the phase angle of the carrier also is the same for both. All right. So we have to maintain the amplitude and the phase angle in this FSK modulation techniques. Okay, there is a condition though that you must be aware of, is that the bit duration is actually n times the period of the first carrier, or n and also m times the period of the second carrier. All right. So what it means is, if you look at the waveform here, all right, so you must have a complete cycle, all right, that lasts for within the bit duration. All right, you must have complete cycle within the bit duration. So in this case, we have 1, 2, 3, 4. We have 4 cycles. All right, that is for binary 1. And then for binary 0, we have 2 cycles. All right, so you must have complete cycles within the bit duration. You cannot send half a cycle or 1.5 cycles. No, you can't. All right, and this is very important for signal recovery later on. Yeah, so this is a condition. Then of course, m and n are different values because the low frequency carrier, if you look at the low frequency carrier, this is 2, this is 4. Yeah. Just to differentiate the binary 1 and binary 0. Okay, generation of FSK. Method number 1, we can straight away make use of the voltage control oscillator. All right, so again, we have our signal data input, which is 1 and 0s. Again, 0 we normally represent with a lower amplitude. So in this case, you can again use the non-return to 0 OOK line coding. All right, so when the amplitude is 0, then the VCO basically produce an output at the resting frequency, which is a lower frequency here. All right, and then when the amplitude of the input signal is high, right, then this VCO output frequency will follow the amplitude, so the frequency will go high as well. Yeah, so this is a direct generation of FSK using a VCO. Method number 2 is actually making use of two separate ASK modulator. All right, two ASK modulator. So these two ASK modulator has two different carrier frequency. All right, so one is F2, one is F1. Yeah. So again, we send our binary signal in. All right. So to actually modulate, use a 1, we use it to modulate this carrier F2. with the frequency f2. All right, so therefore, if we have a 1 here, then this 1 will actually multiply this carrier, give you this carrier component. Yeah, but if we are transmitting a 0, all right, 0, if you send it to this carrier, 0 multiply with this will give you 0 output, isn't it? Which is this one over here. Yeah, but a 0 will we actually use this path, the second ASK modulator to actually modulate the second carrier. All right, so we pass this digital information through an inverter. All right, so the output of inverter basically will invert the input signal, right? So a 0 will become a 1 here, correct? Yeah, so a 1 multiply with the cosine of 2 pi f1t, then you have a carrier over here. Yeah, but if the binary signal is 1, after inverter, it become a 0. So 0 multiply with cosine, you got nothing. Therefore, a 1 will have no output, you 0 output as far as the second multiplier is concerned. Yeah, then after that, we just add these two output together, and that will produce our binary FSK wave over here. Okay, concept-wise, again, is very simple. Method number 3. In method number 3, we actually generate the FSK signal by switching between two distinct frequency sources. All right, so again, we have two sources here. One is with the frequency omega 1, the other one is the frequency omega 2. All right, we use our digital data as a control to the switch. All right, to switch between either this or this. All right, so let's say if it's 0, then the switch will be connected to here. Then we have output this. All right, and then if it's a 1, binary 1, then the switch will be connected to the bottom. Then we have this output over here. All right. Problem with this switching method is that you will have some phase discontinuity over here. All right, and this phase continuity here will actually give you a wider transmission bandwidth. Okay, so that's for FSK signal generation. Again, if you were to look at the spectrum, all right, so the digital signal, all right, I represent it with the VDT. So this one, I actually use it to modulate cos omega 2. All right, basically this is to convert my binary 1 into a set of cosine wave. Yeah, and then the inverter, remember the inverter? So inverter meaning the output of inverter I represent with the VD prime. And basically this is 1 minus VDT lah. Yeah, this is the inverted version. And I use this signal to actually modulate the second carrier with the frequency omega 1. Yeah, this is to carry my binary 0 information. All right. So the ASK output, the FSK signal, basically is a sum of these two. All right. Cos omega 2t multiplied with my digital data and the cos omega 1t multiplied with the inverted version of my digital data. Yeah. Again, if I were to put in the Fourier series expansion for VDT and also VD prime, all right, the difference between VDT and VD prime is only the sign. All right, because they are all rectangular pulses. So again, the Fourier series expansion are very similar, except that the sign is different in between. Plus become minus and minus become plus. All right, so that will give us a set of signal here. All right, this is your half cosine omega 2t. And then the product again will give you this one is a lower sideband. This is the upper sideband for the first harmonic. All right, and also the here the second set of lower sideband and also upper sideband for your third harmonic. And then for fifth harmonic, you also have a pairs of sideband, 7 harmonics. All the odd harmonics, you're going to have sidebands. All right, 2 pairs of sidebands. That is for the binary 1 modulated signal. Yeah. For binary zeros, you have another series here. Yeah, this is a half of cosine omega 1. And again, you have a set of, this is the lower sideband and upper sideband for your odd harmonics. Yeah, for all the odd harmonics over here. Okay, so for as far as the frequency spectrum, if you were to plot it, all right, you're going to see that the ASK, we can actually view the spectrum for FSK as as a spectrum of two ASK. All right. So this one, we have a spectrum for ASK number 1. All right. And then we also have a set of spectrum for ASK number 2, which is this one over here. All right. So we add these two spectrum together. So that will give us the composite FSK with a spectrum, which is this one over here. All right. Yeah. The dotted line. So you can again expect the spectrum for 2FSK to be very, very wide as well. Yeah, the ASK bandwidth is already wide. Now we have two ASK waveform. All right, so that means the FSK's bandwidth is going to be even much wider. Yeah. So again, the bandwidth of the FSK, all right, basically is two times the bandwidth of each ASK, all right, plus 2 delta F, all right. Delta F is actually the frequency separation between F1 and F2, the difference between F1 and F2, all right. So you can see that from this spectrum is that you must make sure, right, in whatever F, if you have chosen your F1, then the F2, you must make sure that the is actually separated with enough distance from F1. All right, your F2 shouldn't be too close to your F1. If it's too close, then these two spectrum will overlap, right? Then there is no way for you to identify F1 and F2 at the receiver. All right, you need to separate F1 and F2 at the receiver later on. Why? Because F1 is carrying my binary zeros. F2 is carrying my binary ones. All right. So therefore, these two spectrum must be separated far enough so that it does not overlap and give you a wrong interpretation at the receiver later on. Okay, and again, the rectangular pulses give us very wide bandwidth. So we can actually, again, pass the rectangular pulses through a low pass filter. Remember we talked about pulse shaping filter. Yeah, this is another type of pulse shaping filter here, which is actually used in practice. It's called a Gaussian low pass filter. All right, so this is actually used in the I think this is quite old technology also lah. The GSM digital cellular mobile system. Okay, this is basically 2G, isn't it? Yeah. So they actually use this to actually reduce the bandwidth requirement for FSK signal. Okay. So recovery of FSK signal, we can actually use non-coherent detection, right? Non-coherent detection, basically we just use filter lah. All right, use filter. So now the incoming signal, all right, so we need to see whether the incoming signal is a binary 1 or binary 0. So that means we want to know whether it's F1 or F2. All right, the signal that coming in, is a carrier frequency F1 or is it F2? All right, let's say now with 0 transmitted at omega C, basically this is omega 1. All right, or F1. All right, so we actually pass the signal through a bandpass filter. All right, that center at omega 1. All right, so what will give us is, if you refer back to this one, if I have a bandpass filter that center at omega 1, so that will recover this portion. All right, so that will recover my binary zeros. So again, I pass it through envelope detector. So it's do I have do I have any pulses at this frequency or not? All right. If there is, then of course they will produce an output. All right. And to actually recover binary one basically now I transmit at a higher frequency, which is omega 2. All right. So again, if I were to pass the signal through another bandpass filter here, this one center at omega 2 or F2, then I can recover my binary one. All right. This is my binary one. Yeah. So again, I pass it through the envelope detector to see whether there is a signal at this frequency or not. Yeah. And then the output of these two envelope detector, I put it into a summing circuit, but the negative one, I pass it through a negative input. The positive one, I pass it through a positive input. All right. So again, the output now will be switched accordingly. All right. So this is my sampling time. All right. I have to sample these pulses at the right time. All right. Meaning I need to sample the pulse here. I need to sample the pulse at this point. Yeah. So if I were to sample the pulse at the right time, all right, then I can pass the pulses that I sample through a thresholder over here. All right. So if the pulse is negative, so that means it's a binary 0 that I receive. And if the pulse is positive, then that means it's a binary 1 that I receive. All right. So again, this is to recover the binary bit information at the receiver. Using non-coherent detection method. Okay, I use 2 bandpass filter followed by envelope detector. Okay, so again, this is possible when we have enough frequency separation. Your delta F is big enough. All right, as I mentioned here, your delta F need to be big enough so that my filter can filter nicely. All right, and the second method is coherent detection method. So coherent detection method meaning I need a local carrier here. All right, because I use 0 to modulate a carrier with frequency omega 1. So at the receiver now, I multiply the incoming signal with a local carrier omega 1. All right, and then after that, I perform integration to see whether I have there is any energy within this as the result of the multiplication or not. All right, if there is, then that means I have a 0 coming out. If no, then I have some energy coming out here. All right, they will tell me this is a 0. All right. Okay, I shouldn't draw 0 here. 0 can mean 0, no amplitude. Okay, and then to recover binary 1, because binary 1, I actually use it to multiply with the carrier of omega 2. So here again, I multiply with omega 2, carrier of omega 2. That should recover my binary 1 if there is. Yeah. So same thing, the output of these two integrator then will be fed into the summing circuit. All right, where 0, the output for detecting 0 going into the negative input of the summing circuit, whereas the output from the binary 1 detector go into the positive side. Yeah, and then same thing I compare here. All right, is my voltage greater than 0? Greater than 0, then that means it's a binary 1 that I receive. Yeah, if the voltage is negative because the zeros go into the negative input here, so that means the binary stream or the bit that I receive right now is actually a 0. All right, if the comparator input is negative. Okay. So again, this slide show you some of the a bit of the mathematical analysis. Okay, so the signal coming in consists of carrier with two carriers with different frequency, right? Omega 1, omega 2. But at any one time, only one of these cosine wave is present. All right. If the incoming bit is a 1, then I only have this cosine wave. If the incoming bit is a 0, then I have this cosine wave. Yeah. But over the entire time duration, I have a combination of these two. Yeah. Now, my R1T basically is this one here. Okay, this one here. So R1T basically is a product of cos omega 1T because I multiply the incoming signal with cos omega 1T. And this is my incoming signal. All right. And I integrate over the bit duration. Yeah. So again, if I perform cross multiplication, then I have cos omega 1T and cos omega 1T, and also cos omega 1T multiplied with cos omega 2T. All right. So again, if I convert this using trigonometry identity, then I have half of 1 plus cos 2 omega 1t because this is cos square omega 1t. All right, then again, this one will give me two side bands, right? The two, what we call two side bands. Yeah, okay. We split into two different frequency, which is omega 1 minus omega 2 and omega 1 plus omega 2. All right. And we integrate this over the bit duration. Yeah. And if, all right, if we actually have an input, which is the incoming signal is actually omega 1, all right, then what you have is this one, you perform integration, will give you half of TB. All right, so your R1 will have an amplitude of half of TB here. Yeah. But if only cos omega 2 is present, you don't have cos omega 1, then your RT, right, that means within this bit duration, you don't have any energy. So it will be 0. All right, it will be 0. And why is that possible? That is possible because the integration of this term, all right, if you look at the bottom here, I actually put a note here. The integration of this term will give you 0. All right, we give you 0. Why? Remember the condition, our bit duration is actually equals to n times of the period of our first carrier and also m times the period of our second carrier. All right, so that will give you full cycle. All right, full cycle, and then the integration of cosine will give you sine, right? Yeah, so sine of 2 pi n 2 pi will give you 0. So you have nothing out here. Yeah. And then the same goes for binary one. All right, so for binary one, which is the bottom part of this circuit here, all right, we multiply with cos omega 2t. So therefore the product, all right, will give you again half of 1 plus cos 2 omega 2t, and then plus again the difference between the two carrier frequencies and the sum of the two carrier frequencies. So same thing. All right. If the incoming signal is a binary one, then of course you have cos omega 2t. All right. So this term now will be valid. Yeah. So you have half of TB at your output. Okay. So let's do a quick summary on the binary phase shift keying. So as you can see, phase shift keying is now less prone to error compared to ASK. Right, because we actually look for specific frequency only. Yeah, the signal is now again encoded in the frequency rather than the amplitude. So any change in your amplitude will not affect the recovery part of the circuit. Yeah. The problem with FSK is the spectrum is very wide. Okay, it's 2 times of the bandwidth of the ASK. It requires very wide bandwidth. Um, However, because it's less sensitive to noise, right, and then so less prone to error caused by noise, then FSK actually is used, all right, and this is commonly used in high frequency radio transmission. All right. Um, okay, so that is for FSK. All right. It's a good time to take a break here. Do you have any questions for before we Or is it hello? Question? No question, then we stop for 1 minute break. Let's see. 1 minute.
Miss, your line is lagging.
My slide is lagging. Oh, so what?
No,
I talk faster than my slide.
no. I say your line is lagging.
Oh, is it? Oh, okay, okay. But you can still hear me, right? And you can see my slide,
Not better already, Miss.
Oh, so could you follow my lecture just now?
Yes, can follow.
Can then okay, good. So we stop for break here, shall we?
Sure, Miss.
Yeah, 5 minutes, yeah. So we resume at now it's 12:05. Let's come back at 12:10. Okay, are we all back here?
Yes, miss.
Okay, so let's move on to phase shift keying. Okay, so as far as ASK is concerned, we represent the binary information ones and zero with two different amplitude, right? Zero, no amplitude, one has certain amplitude, right? And then for FSK, we send our zero and ones using two different frequencies, yeah? And then for phase shift keying, the concept also is very similar, except that now we send the binary information with two different phase angle. All right. So if you look at the expression on the right hand side here, all right. So the FS or the PSK signal, all right, will have again will be it's a cosine signal again. It's a sinusoidal wave again. But then the phase angle now depend on the binary information. Yeah. To send a binary one, let's say for example, to send a binary one, I send a cosine wave with zero phase angle. And then to send a binary zero, I'm going to send the same cosine wave with the same frequency, but now the phase angle is different by 180 degree. So this is pi. Yeah, 180 degree. And therefore, cosine of 2 pi fct plus pi is actually minus cosine 2 pi fct. All right. So the waveform is going to look like this. All right. So I send a 1. Again, this example is a sinusoidal, like easy to draw. So it's a sign. All right. And then binary 0 is sent with a negative sign. All right. So the phase angle is 180 degree apart. 180 degree because there's a furthest phase angle that you can have between two carrier signal. All right. So as far as PSK is concerned, the amplitude stay the same. The frequency also stay the same for these two. Yeah. Um, so again, when I say this one, the phase angle is in this example, we send one with a 0 degree phase angle, and then one is 180 degree phase angle. Okay, so if you were to look at this signal amplitude here, so it's the same as we actually multiply the carrier with amplitude with a plus, all right, with the plus one amplitude and the minus one amplitude when the information is 0. Correct or not? Yeah. So therefore, to actually modulate a carrier using PSK, your binary waveform need to be a polar signal. All right, it need to be a polar signal, meaning it need to have positive and negative amplitude. All right, so with that, the first method to generate PSK signal again is by switching the sign of the carrier using the data input. All right, so we have a carrier here. All right, and also have another version of the carrier here, which is 180 degree, has a 180 degree phase shift. Or basically, we invert this cosine, and we get minus cosine. Yeah, then the binary information here, we use it as a data input that switch between these two waveforms, either sine or minus, either cosine or minus cosine. All right, cosine or minus cosine. All right, so that will give us this. Yeah, so this is, in this case, again, the waveform is sinusoidal rather than cosine. All right, so again, this is for minus, it represents 0, and this is for 1, that represent, this is positive, that represent a binary 1. Right, so very easy modulation technique. And the second one, okay, if you want to use filtering, All right, meaning why we need filtering? Because if you look at this rectangular data input and you actually switch between two different carrier, then again you end up with some white bandwidth here. Okay, you end up with some white bandwidth here because during the switching. So if we are going to use filtering and we want less bandwidth for transmission, then we can actually do multiply. We can actually modulate by using multiplication. Again, this is similar to our double sideband suppressed carrier modulation technique. We multiply our digital data with a carrier signal. Yeah. But if you want a lower bandwidth, then of course the digital data, we actually pass it to a pulse shaping filter first. All right, so that will reduce the bandwidth of our data, and then that will be less bandwidth for the PSK signal. All right, and then if you want to use multiplication technique, then make sure your data input must be bipolar. Bipolar meaning you have positive and negative. All right, positive 1 volt for binary 1, negative 1 volt for your binary 0. All right, so this is for binary 0, this is for binary 1. Yeah, then the product of course will be of again positive 1 will give you a positive, so this is for 1, binary 1, and this one will be for binary 0. All right. Okay, for PSK, all right, for PSK, the demodulation part, only coherent detection method can be used. All right, only coherent detection method can be used because we need to detect the phase angle. All right, phase angle detection require the coherent method. So again, because it's coherent, that means you need to have a carrier phase that is synchronous to the carrier phase at the transmitter to be available at the receiver. Yeah, so that's the same thing. So any phase error, all right, could reduce your signal output by a factor of cosine theta. All right, any phase angle theta will reduce the output by a factor of cosine theta. Why this? If you cannot remember, refer to chapter 1. I think I talked about this in chapter 1. I don't know, the amplitude modulation chapter. Okay, you refer to that chapter. I talk about this here, there. And then if your phase angle is 90 degree, then your output will be 0. You have 0 output. All right, so that means you are not able to detect whether this is a 1 or this is a 0. Okay, right, so this slide actually explain the demodulation method for binary PSK. On the left-hand side is the mathematical analysis. So now at recovery, we multiply the incoming signal or the modulated signal by the same carrier. So in this case, by 2 cosine of 2 pi FCT. All right, so it's the same phase and same frequency as the incoming signal. Right, our modulated signal can be plus A cosine or minus A cosine. All right, plus A cosine meaning it's a binary 1, minus A cosine meaning is a binary 0. All right, so if you were to multiply this with this, all right, so that will give us 2A cosine square 2 pi FCT. All right, and then if we were to convert this cosine square into half of 1 plus cosine 2A, this is again using the triple identity. Then you have a of 1 plus cosine 4 pi FCT. All right, if the incoming signal is a binary 1. So you're going to have an output with the DC value A, all right, plus this is a high frequency cosine signal, high frequency component here, which is at what, 2FC. Yeah, and then if it's a binary 0, then the product, the output of the multiplier will give you a DC value of minus A, all right, plus again the high frequency component here. All right, so how do we recover the signal? just by removing this high frequency component, right? Yeah, by using a low pass filter. Yeah, block the high frequency component with a low pass filter, then we can recover our original baseband. Either is plus A or minus A. Plus A is for 1, minus A is for 0. All right. So basically, this is how the demodulation part look like. Yeah, this is the incoming signal. This is a local carrier. We multiply. Then we use a low pass filter. All right. Cut off frequency of the low pass filter. Cut off frequency of the low pass filter. How do we determine? It's a baseband frequency of your digital data, right? Yeah. Okay, and then on the right hand side, okay, we have some diagram that actually illustrate the concept. So now the information we want to send binary is in this form, 101101. All right, and this is a binary code. So we use polar coding here. So the baseband signal now for a binary one, we use a positive pulse. Again, this is a non-return to zero polar line code. Yeah. So 1, we use a positive pulse. 0, we use a negative rectangular pulse. All right. So 2 ones, then continuous, right? 0, then this is 1, this is 0, and then back to 1 again. Yeah. So to perform PSK using multiplication technique, you have to make sure your digital data, right, is converted into non-return to zero polar coding. Right. You can also do return to zero polar coding. Later on, you see in the, I believe I discussed it in tutorial, then you're going to see that your bandwidth requirement is more. But if you use non-return to zero, your bandwidth is less. Okay, then the modulated signal. All right, after we multiply this baseband signal with the carrier, the cosine wave, or in this case, the sine wave, then you're going to get your sine wave, your modulated signal in this form. All right, and this is the, for negative, then you have your minus sign, all right, and plus sign and so on. So that's your modulated signal. Okay, multiply. After we multiply the incoming, this modulated signal with a local carrier here of the same frequency and same phase, then the output waveform is going to look like this. All right, you can see now the carrier frequency now is 2 times. All right, which is this term here. This is your cosine term here. All right, and then the envelope will be your DC, the DC value. All right, plus A or minus A. Yeah, and then after passing this signal through a low pass filter, that basically remove your this high frequency component here, and then we recover our baseband signal. All right. So if you understand AM, FM, this ASK, PSK, FSK is actually very, very simple already. Okay. All right. So what are the advantages of PSK? Again, it's less sensitive to error, less likely to have error because it's less sensitive to noise. Yeah. Compared to ASK. And then the bandwidth is the same as a ASK bandwidth. All right. How do you know it's the same? Because we generate the PSK signal using the same technique as ASK. We just multiply our line code for binary information into with a carrier signal, right? Again, we use the same double sideband suppressed carrier modulator to do it. Okay, so PSK actually is better than ASK because it's less sensitive, less prone to error, all right, less prone to noise, and it's better than FSK because it actually uses less bandwidth, all right, as compared to FSK, correct? FSK need at least 2 times the bandwidth of ASK, all right? That means FSK need also at least 2 times the bandwidth of PSK, right? So PSK actually has is better than these two in different aspects, but these are what we are what we're actually concerned with, right? One is the how likely is noise going to affect our signal and then cause error in detection. And the other one is how much bandwidth is this signal going to occupy. Yeah. So PSK is better than these two. The only problem with PSK is that the signal detection is more complex because you need synchronized detection. All right, that is the only problem. You need synchronous detection. And therefore, as far as PSK is concerned, to ensure that the local carrier at the receiver is synchronized with the carrier at the transmitter. Most of the time, PSK is used for wireless communication over short distance only. All right. FSK can be used for long distance wireless communication, but PSK is normally used for short distance wireless communication. And that's why you see PSK being used in RFID system, in Bluetooth, as well as in the local network. All right. It's for short distance uh, wireless transmission. All right. Okay. Any question on PSK before I move on? No? No, then I move on, yeah. Okay, so the next one I'm going to talk about is differential PSK or DPSK in short. So differential PSK is a non-coherent version of PSK. All right. You remember the disadvantage of PSK, the main disadvantage of PSK is that you need the transmitter and receiver carrier frequency and phase to be synchronized. All right. And then differential PSK basically solve this problem. All right. We don't really need phase synchronization. Yeah. Because we use differential coding. Yeah. So what does differential coding means? We actually encode the information in phase difference between successive signal transmission. All right. So normally we start with the reference phase angle, and then to send a zero, for example, to send a zero, we actually advance the phase of the current signal by 180 degree. So meaning if the current signal, the phase angle is 180 degree away from the previous signal, so that means the current signal is a zero. All right. And if the phase of the signal remain unchanged, that means the current bit or the current signal is a binary one. Yeah. And of course, we must know the this is only possible, all right, provided that the phase error, right, the phase error contained in the received information is changing slowly. All right, so that means as far as the two successive bits is concerned, all right, there isn't much change between the phase error. And this is actually quite possible because 2-bit interval normally is very short time. All right. And then unless you have a, a big noise or certain sudden rise in the noise that actually change the phase angle of your signal. Otherwise, this can be maintained easily. All right. So with the phase angle, phase error between the 2-bit interval is very small, right? So the phase difference between the 2 bits, right, actually will be a true representation of the actual phase difference, all right? So actually it will be independent of theta. Okay, I think if we illustrate, I think it will be better, isn't it? Okay. I have half an hour for this, so let me see. All right, so this slide actually will show you how a DPSK signal can be generated. Yeah, so step one is actually do a differential encoding of the binary bits. Yeah, we do this by using a XNOR gate. XNOR gate is a what? A uh, exclusive NOR, and then with the inverter on the outside. So that means this exclusive NOR gates, all right, if the two input are the same, all right, is going to give or produce a one at the output. See now, if the two input are the same, it's going to produce a one at the output. If the two inputs are different, then the output will be zero. All right. So we one of the input to our XNOR gate is the incoming message, the current bit, and then the second input is the previous bit. All right. So basically, we delay a bit by delay the message by one bit. So we compare. All right. Compare the current bit with the previous bit. Okay. So now let's look at the information sequence given here. So I have my current bit, which is 1. All right. And let's say I choose, in this example, I choose the initial bit as 1 as well. All right. So 1 exclusive NOR with a 1 will give me a 1. All right. Which is this one here. Yeah. And then the second bit is a 0. All right. 0 exclusive NOR with this one. This now exclusive NOR with this will give me a 0. All right. And then the next bit, 0 exclusive NOR with the previous bit, which is 0, will give me a 1. Okay. Maybe I should mark here on the diagram as well. This is your MI. Okay. This is your DI. And this is your DI minus 1. All right. So this is your, if I'm talking about this bit, then I'm going to compare with this bit. All right. That will give me this bit. Yeah. So this is my DI. This is my DI minus 1. This is my MI. Okay. This is my I. Yeah. Um, then followed by, after I get my strings of DI, all right, then I do a level shift here. All right. I do a level shift. All right, that means here I need to represent my ones and zeros differently. So a binary 1, I'm going to shift it by make it positive. A binary 0, I'm going to make it negative. All right. Therefore, my output here will be plus minus 1. Why? Because I need a polar signal. Polar signal so that I can multiply with the carrier. Right. So 0 will be negative amplitude, and 1 will be positive amplitude. All right. Then I multiply here, so that will give me positive, negative A cosine omega CT. Yeah. And so if I were to translate it to the cosine wave over here, so you can see 0 will become minus, will give us minus A cosine omega CT. So that means we actually have a pi phase shift here, a phase shift of pi radian, which is 180 degree. Yeah. So that means 0, I transmit with a 180 degree phase shift. And this is my differential coded sequence. I actually use this one to multiply with the cosine wave. All right. So 0 we send with the pi, the transmitted phase will be pi. 1, the transmitted phase will be 0. Okay. So this is how we generate a DPSK signal. All right. This part is the same as PSK. This part here is the same as PSK. And then the one before is the one that we actually perform differential encoding. All right, step 2 is your PSK. So this part actually is your PSK. All right, this part is your step 1 here. We do our differential coding. This is your step 1. Right, this is your step 2. Okay, level shift is just to make sure that our amplitude of the signal has positive and negative values. Yeah, we must make sure it's polar before we multiply. Okay, so that's for generation. And then for detection, okay, so again, for detection wise, the receiver actually compare the phase of the incoming signal with that of a previous signal. All right, so now we have incoming signal, we also have the delay version. All right, so this is your RT and this is your RT minus TB. Okay, we multiply these two and then we differentiate. All right, and no differentiate, like integrate, sorry. We integrate and then the result of integration, we actually, okay, I actually put down the equation here. So we multiply RT with RT minus TB and then we integrate for that entire, throughout the entire bit duration again. So now if my RT, my current bit is a cosine omega CT plus, again, this is my phi. Okay, phi k is the phase of the current bit. All right, theta is the phase error. All right, it's a phase error. And I multiply with the previous bit. All right, previous bit, which is cosine omega CT again. This is your the phase angle of the previous bit. All right, and again, as I mentioned previously, we assume that the phase error is the same for these two successive bits. Yeah, meaning from one bit to another bit, the phase angle didn't, the error was the same throughout for these two bits. Then you see that the output, right, the output y basically is proportional to the cosine of the difference between these the two phase angle. All right, which is the phi k minus phi k minus 1. All right, so now in this derivation, that actually tell us the unknown phase, which is the error, now become irrelevant. Yeah? As long as they are the same, it become irrelevant already. Then we just need to know. All right, the next thing we just need to know what is the phase angle between these two successive bits. All right, or these two successive carrier. Yeah. So now if the phase angle are the same, wait, right? That means this the previous angle minus the current angle minus the previous angle is 0. That means we actually receive a bit 1 here, a binary 1. All right. So again, cosine of a 0, if these two are the same, that means the difference is 0. Cosine of 0 will give us a 1, right? All right, a positive values. Then your y will be greater than 0. All right. However, if the phase angle between the two carrier is pi, which is 180 degree, then we know actually we actually send a bit 0. All right, or binary 0. Again, cosine of a pi is actually a negative value, right? Cosine of 180 degree is minus 1, correct? Yeah. Then your y produced here, the output of your integrator, will be a negative value. Yeah. So we pass this y through a comparator with the threshold set at 0. Yeah, so any positive value, which is y greater than 0, is actually a binary 1. All right, will give us the output back, which is 1. And then any values that is less than 0, which is negative, represent a binary 0. Okay. All right, so this slide actually show you the same data again. So the one we transmitted just now is this one. All right, the one we transmitted just now is this one. And then 1 bit delay. All right, 1 bit delay over here. This delay, yeah, will give us this string. Yeah, 1 bit delay. So this one is delay to here. This one is delay to here. This one is delay to here. All right, and then the difference in phase, 0 and 0 is 0. Pi and 0 is pi. 0 and pi is also pi. Right. So they actually show you the difference in the two phase angle. And y, again, the output y will depend whether it's the difference is 0 or pi, right? Cosine of 0 will give you a 1, cosine of pi will give you -1, right? And so on. Then you pass y through the comparator, right? A positive value will give an output of 1, a negative value will give an output of 0, right? So you can see whatever we transmit previously here is now received correctly here. Okay, these two. Okay. So you can see in differential phase shift keying, in the recovery part, we don't need any local carrier. There's no more carrier required over here. All right. We just need to delay. We just need a 1-bit delay, and then we multiply them together. All right. The incoming signal with the signal that has been delayed by 1-bit duration. We multiply them. We pass it through an integrator, and then followed by a comparator that will give us the originally binary information. Right? No carrier is used over here. Okay, so that is for differential detection. Okay, for differential detection. Quiet. Quiet, I presume no problem, huh? Okay, then let's talk about quadrature PSK. Quadrature PSK basically talk about 4-level PSK. All right, quadrature, again, we talk about 90 degree. The phase shift is 90 degree from each other. So that is meant by quadrature. So here, in QPSK, we can actually code 2 bits into one signal element. So what it means is we use one cosine wave, all right, one carrier signal to actually carry 2 bits. All right, one carrier signal to carry 2 bits. So if the phase angle is 0, that means this carrier is actually carries binary 0, 0. All right. If the incoming carrier signal has a phase angle of pi over 2, 90 degree, that means this carrier signal is carrying binary information 0, 1. Yeah. And if the carrier signal has a phase angle of pi, so that means this carrier signal is carrying binary information 1, 0. All right, the same go for the last one. If the phase angle is 3 pi over 2, then that means this carrier signal is carry binary information 1, 1. All right. So it can be this or it can be any phase angle as long as the phase angle between two different carriers is 90 degree apart. All right. It can be any. So it doesn't need to be okay, 0 and then followed by pi over 2, followed by pi, followed by 3 pi over 2. All right. So in this case, you can see that we actually use 4 different phase angle, all right, to carry each of them carrying 2 bits of information. All right. So in this manner, we can actually increase our bit rate. So increase instead of one cosine signal carrying 1 bit, now we use one cosine signal to carry 2 bits. Yeah. Okay. Then in a similar manner, if we actually use a smaller phase angle in between, then that will allow us to actually increase to more levels. All right. So if we increase to 8 levels, then this binary information that we can carry or each carrier can carry will be 3 bits. Yeah. And that will increase our bit rate to 3 times. Yeah. But however, if you use a higher rate, then that means you must make sure your equipment can actually differentiate the small difference in phase angle. All right. Because in total we have 360 degrees, isn't it? Yeah. If you want to have 4 different levels, 360 degree, 360 divided by 4, so that will give you 90 degree, right? Divided by 4, so that will give you 90 degree. Yeah. If you want more levels, let's say I want 8 levels. So I divide by 8. So that will give you what? 45 degree, right? Yeah. So if you divide by 16, I say I want 16 levels. So that will give us 22.5 degree. So the more levels you use, because how far you want more level? Because the more level you use, you can actually represent more bits. Therefore, that will increase your bit rate. Yeah. But however, the problem is, can your equipment differentiate the small difference in the phase angle or not? Okay. So that is a limitation of hardware. Okay, so constellation diagram is actually very important in PSK. All right, constellation diagram actually tell us the amplitude and the phase angle of the signal, all right, or of the each carrier. So this example over here, okay, if you have the amplitude, right, you have the quadrature component. So that means we have the in phase carrier, we also have the out of phase carrier. We call it a quadrature carrier. All right. So where your dot is will actually tell you your amplitude of the I component as well as the amplitude of the Q component. All right, the amplitude is actually, again, use Pythagoras theorem that will give you the square of this plus the square of this, and then root it, you get the amplitude of your the actual amplitude of the carrier signal. All right, and then the phase angle of the carrier signal is this. This is the angle. All right, so to put you in perspective, all right, let's look at ASK. ASK, you can also look at the phase. But again, as far as ASK is concerned, the phase angle is 0. All right, we just transmit a binary 0 with 0 amplitude, and we transmit a binary 1 with a certain amplitude. All right, yeah, and if this is A, then the amplitude of your carrier signal is just A. All right, and then for BPSK, BPSK meaning we transmit 1 with a carrier of a certain amplitude. All right, the phase angle is 0. This is I transmit my 1. But I transmit 0, a binary 0, with the carrier of the same amplitude, but then the phase angle is now pi, 180 degree. This is pi. Okay, so this is for binary PSK. The dot here, the distance from the origin will tell you the amplitude. All right, so same thing. Binary 0 and binary 1 are actually sent with a carrier of the same amplitude, but the phase angle is different. Binary 1 is sent with a 0 phase angle, and binary 0 is sent with the carrier with a 180 degree phase angle, or pi. Yeah. And then for QPSK, we actually divide 360 into 4, right? Because it's actually, we need 4 different phase angle for the carrier. Yeah, and this is just an example. Yeah, so we'll in this case, binary 00 is sent with the carrier of this amplitude. Wait, let me draw. This is the amplitude of the carrier. This line will tell you the amplitude, and then the phase angle is this one here. All right, you can either read it from here or you read from here lah. If you read from here, then what is this? 180, this is 270. So between 180 and 270 is what? 225, right? So this is 225, isn't it? Yeah. Then 01, 01 is sent with the carrier, again, the same amplitude. Yeah, but then the phase angle now is 135. Yeah. And then 11 is sent with the same amplitude, carrier with the same amplitude, but the phase angle is 45 degree. Yeah. And 10 is sent with the carrier of the same amplitude, but the phase angle is minus 45. All right. So basically, you can send your signal, your carrier with any phase angle, as long as the difference between the 4 different carriers are 90 degree. All right. So as long as they are 90 degree apart, then that would be easier for your detector or the receiver to actually detect the phase angle and then work out um, what is the binary information that is receiving. Okay, so that is for constellation diagram. Yeah, actually this diagram show you that for QPSK the phase angle can be anywhere. Okay, you can start with the one here, and then the next one has to be 90 degree apart. Next one also 90 degree apart, and so on. You can also start here, right? Start here, and then the next one is 90 degree, 90 degree. As long as all these four symbol, we call it symbol actually, 90 degree apart from each other, then this is a QPSK. Okay, so as I mentioned previously, because if we use QPSK, we can actually send 2 bits of information with each carrier signal. All right, so that means it actually increase the bit rate. All right, it actually increase the bit rate. That means using the same bandwidth, I can transmit 2 times more bit. All right, so I can transmit instead of sending in the same bandwidth, instead of sending 1 bit, now I can send 2 bits, right? So that actually increase the efficiency of the bandwidth of as compared to BPSK, right? Um, okay, and then what else? Okay, QPSK. No, this is 8PSK. So 8PSK, as the name suggests, we have 8 levels. So 8 levels, we need 3 bit to, that means each carrier component or each carrier symbol actually carry 3 bit of information. All right. Where does 8 come from? 8 comes from 2 to the power of 3. All right. 2 to the power of 3 will give you 8. So that means each carrier now is carrying 3 bit of information. Yeah. So again, this is just an example. So if the incoming signal, the carrier signal has a 0 phase shift, that means the binary information that is carrying is actually 000. It's carrying 3 bit here. But if the incoming carrier signal is has a 45-degree phase shift, then that means this carrier signal is carrying binary data 001. Yeah, and the same goes for the rest. Okay. Then comparing QPSK and APSK, all right, with BPSK, is that QPSK and APSK actually are more bandwidth efficient. All right, because using the same carrier signal, we can actually send more bits. Yeah, so that is more bandwidth efficient. And so for QPSK, we are actually sending 2 bits per symbol meaning per carrier. All right, and then the 3 bit is for APSK. All right, so in this case, we are actually able to transmit with a higher bit rate. All right, so the same bandwidth, but we can we can transmit more bit rather than compared to BPSK. All right, and then for QPSK and FPSK also, because we always have a phase change between symbols, so that the phase change can actually give us the clock information at the receiver. All right, but the only problem is the receiver is more complex because it need to be able to distinguish between for BPSK it's just no positive and negative only, right? So you don't really need to differentiate the phase angle. But then for QPSK and APSK, you usually need a receiver to actually differentiate the phase angle. Okay, application wise, QPSK is also used in for cellular wireless standards. Okay, GSM, CDMA, and so on. All this. All right. Um, that's for the benefit. What for benefits for higher bit rate. All right. Um, all right. So QPSK is more widely used because of its bandwidth efficiency compared to BPSK. But PPSK is easier to implement and detect. All right. All right. Any questions before I think I want to fit course. Stop here already. I have another class starting in 2 minutes. Any questions?
No question.
Very good. So all right. So you need to familiarize yourself, yeah, with these three types of digital modulation techniques, and that will help you in your practical session later on this week. All right. And again, I think it will be really beneficial for you if you go through the lab manual first before the lab session. All right, that will give you a better idea on what you are going to do. All right, and to prepare yourself in case you do not understand the concept well. Yeah, is that all right? Okay. So
Okay, miss.
I see you later then. Bye bye.
Bye, miss. Thank you.